Welcome viewers to another video of Smart Pathshala. So today we are going to learn about differentiation, right? Differentiation. Pardon my handwriting. Okay. So first of all, we need to know why we study differentiation. What are the applications of differentiation? Okay. Now, in this video, we'll learn about this thing. What is differentiation? Where do we apply it? What is the physical interpretation of a differentiation? And what is the geometrical interpretation of differentiation? Right? Okay. Now, suppose we have a function y is equal to f of x. Right? Before this video, I urge every one of you to check my videos on the continuity and differentiability, because when a function is continuous and differentiable, then only it can be used in this chapter, right? So let's suppose y is equal to f of x be a function, right? Now, differentiation is such a process by which we measure, okay? Mind this thing, that differentiation is a process, right? This is a process. This is not a certain types of value that you will get as a result, right? After differentiation, the thing you will get is called derivative, right? Okay. Now, if y is equal to f of x be a function, then differentiation is the process by which we measure the rate of change of this function f of x with respect to x, change in x. Now, suppose, write this thing, that the process to measure rate of change of f of x with respect to x, with respect to change in x. Or you can certainly write only with respect to x. With respect to x is the differentiation, right? Pause the video and note it down. Now, not only note it down, but memorize the meaning, because this differentiation is a process to measure the rate of change of the function f of x or rate of change of this y with respect to x, because x is the independent variable here and y is the dependent variable here. Now, suppose with respect to x, right? এবার আমরা কি করলাম? We have two variables x and y. Okay? Now we increase this value of x by some amount del x, right? Del x. Okay. Now what is the new x? New x become x plus del x, obviously, right? Now, when this term is x, then we have y is equal to f of x. Now, when we increase x, when the new x become x plus del x, then what is this y? This y will not be same, obviously. This y will become y plus del y, where del y is change in y. You can write y plus del y as f of x plus del x as well. Now, what we have said earlier, that rate of change of f of x, okay, with respect to what? With respect to x. Now, so rate of change of x, rate of change of f of x with respect to x is equal to, okay, cool, is equal to rate of change of f of x. What was the, so we'll write here the new f of x minus old f of x. Hence we will get the change new f of x minus old f of x. Then we will write new x minus old x, right? Because we are calculating the rate of change of f of x with respect to x, change of f of x, that is change of this with respect to change of this, right? That is equal to, so new f of x is f of x plus del x minus f of x, old x is this one, f of x on new x is this one. So new x is what? X plus del x minus old x is x, and here we can write f of x plus del x minus f of x by del x, right? So this is the rate of change of f of x with respect to x. Now if I write in this direction new f of x, we can write f of x as y, right? So this is y, sorry, new. So new means this one, not this one. This one is old. So y plus del y, new one, minus old one. Old one is this one. So y minus new x. What is new x? X plus del x minus x. So we are having here del y by del x. We can write del y by del x. Okay? Note it down. Now, if in a certain condition where the change, what is the change? The change is this del x. If in some condition, if this del x is tending to 0, which means this del x is very, very small, for a very small increment or decrement in x, right? Then what we will find out? We will have obviously limit. Limit what? When del x tends to 0. When del x tends to 0, then the value of this term, the value of f of x plus del x minus fx by del x, right? When this del x is very small, that is, it is tending towards 0, then we can write this del y by del x as dy by dx, right? Perfect. Now, cool. So we have derived this thing. Now it is also written, now this process, okay, this process by which I get this thing, this process is called differentiation. And the result I get after this differentiation process is called derivative. Notice these two terms, one is differentiation, another is derivative. These two are not equal terms. These two are really different terms. One is process, one is result, right? One is the cause, one is the effect, right? Differentiation. Now we also replace this del x by h. So when del x is tending towards 0, then obviously h is also tending towards 0. So we write limit h tending towards 0 f of x plus h minus fx by h can also be written as dy dx, or better if you write d of f of x. This is also written in this form, f dash x. Okay, this is also written in this form f dash x. Now, in this time, suppose you have been asked to find the derivative of a certain function f of x at some point x is equal to a, right? At some point x is equal to a. Cool, you can do this. How? Just put in place of x, just put a. Where you need to put this? In this definition only. Limit of h tends to 0, f of x plus h minus f of x divided by h. Just put the value, okay? So after putting the value, what I obtain? Let's see. What I get is f dash of a is equal to limit h tends to 0, f of a plus h minus f of a divided by h. This is what I get after putting x is equal to a, because I am trying to find out the derivative of f of x at the point x is equal to a, right? Now, remember, if I put a plus h as x, suppose I am substituting this thing as x. Now, when h tends towards 0, then obviously x is also tending towards a, which means I can write in place of h tends to 0, I can write x tends to a. And in place of x, in place of h, I can write from here h is equal to x minus a, x minus a. And here f of x minus f of a. Perfect. Now, so this f dash a, right? So this is another definition of derivative at a certain point x is equal to a. That is, if you are asked to find out the derivative of a certain function at a certain point x is equal to a, then you can also use this definition, right? Okay. Now it's time so that we can learn about the physical interpretation. So this was the mathematical interpretation. Now we'll read about the physical interpretation, and then we'll go to the geometrical interpretation. What is the physical interpretation? Okay. The physical interpretation means, the term physical means something we can imagine, something we can calculate by our practical views. So suppose we have 2 points. One is here O, and this is going towards X, right? I have a motorcycle, and I have two variables, like two parameters. One is distance d, or you can say displacement, time. Time is another thing that I have. Now, I want to ask you a question. Which one is dependent variable here? Dependent, right? Obviously, d is dependent on time, because time is independent variable of this t. Now, the amount of distance I go is totally dependent on the amount of time I travel if I have a uniform velocity, right? If you maintain a velocity v is uniform velocity. Uniform velocity. If you are having uniform velocity, okay? Now, suppose this is at a certain point P. You have traveled at certain point P, right? So, the distance is given by, suppose you have d as distance. So, distance must be a function of t, right? Okay? Satisfied or not? Because the distance depends on the amount of time you have traveled with the velocity v. Okay? So, the distance is obviously a direct relation. That is, it's a function of time t. Perfect. Now, suppose at time t0, right? At time t0, I have traveled a distance of f of t. Right? I have traveled a distance of f of t at time t0. Remember, this is time, this is the distance, this is the time. So, we have OP as f of t0 in t0 time. Right? Now, suppose I travel from this point P more h time. I am here now at this location. I travel more h time. Suppose h minute, second or hour. Right? So I go to at this point Q. So at this point Q, the time becomes t0 plus h. And if the time becomes t0 plus h, then the distance becomes f of t0 plus h. Obviously, the distance becomes f of t0 plus h. So, what is OQ? OQ is f of t0 plus h. Right? OQ is f of t0 plus h in t0 plus h time. Now, let us calculate the velocity. Now, velocity to travel from P to Q, this distance. So, obviously, what is the velocity of this distance? It obviously velocity is distance PQ by time. What is the time? Time is this distance h. Because when I was here, the time was only t0 time, right? Then I traveled more h time, which means the distance will be h. Okay, now we can write PQ as OQ minus OP by h. So OQ, I can write this term, that is f of t0 plus h minus f of t0 by h. Right? I can write this thing. Now, hold it. At this point, suppose as this time t, this time h, suppose h time is very, very close to 0. Okay? Now, as h tending towards 0, which means in no time, in very infinitesimal time, this h is tending towards 0, then obviously q will also tends towards P. Right? Q will also tends towards P. Hence, if the Q is also tending towards P, I mean this will be like this much. Very small. You can't detect it in the naked eye. Now, so I have instantaneous speed. What is the instantaneous speed? When h tends to 0. Now again I come to tending towards 0. So that means I have to calculate this velocity using limit h tends towards 0. I have f of t0 plus h minus f of t0 by h. Right? This is the instantaneous speed we have to calculate, already done. Now, you must now see, notice, or rather say you must notice that we were having a function f of t. This was the distance t, right? Now at t is equal to t0. Now what can you write this thing? From the mathematical definition of derivative, we can write, no, we can write that if f is the function, then we can write f dash of t0, right? F dash of t0, because in place of x we have t0 here. Perfect, no? So this is what instantaneous. We can say that if, remember this is the physical definition, if t is equal to f of t, t is equal to t0, right? T0 is something time and t is a time variable. Then differentiation of f of t or f dash t, differentiation of f of t or f dash t at certain point t is equal to t0 gives the instantaneous velocity of the object, okay, at t is equal to t0. Now if distance is given by the function f of t and t is equal to t0, then differentiation of f of t at certain point t is equal to t0 gives the instantaneous velocity of the object at t is equal to t0. So this is the physical definition of differentiation. Now let's study the geometrical definition. Remember, every certain point in this universe can be designed or can be defined by geometry, because geometry is a such element of mathematics. It's such a beautiful element of mathematics that you can define anything with the help of geometry. Now the geometrical approach. Let us define differentiation using the geometry, right? So let us plot a graph. Suppose we have y-axis here and here is y dash axis, here is x dash axis, x-axis, sorry. Okay. Now we are having a curve goes like this. Okay. Perfect. We can have. Now the thing is that the equation of this curve is f of x. We can write it y. Suppose f of x. F of x can be anything. Sin x, cos x, blah blah blah, log x. Okay. Then suppose here the point is x is equal to c. Now at x is equal to c, what is the value of y? Now obviously I will go straight here. So this is, you can write it here. This is the point P. Now how can you calculate this term? Look, this term is nothing but f of c. Got it? This term is f of c. So the coordinate of P is what? C and f of c. Right? Okay, perfect. Now, if I go further at a point here, suppose. Now this distance is h. So x here will be c plus h. Now, what is the value of y at this point? And this point is nothing but q. So q had the coordinate of c plus h as x and f of c plus h as y. Right? Now, everything is good. Now let us calculate the slope of this chord PQ. What can be the slope of this chord? Okay, let us draw perpendicular here. So this point, let us name it as M. Right? So this is the chord. Right? This is the chord. Okay. Now the slope of the chord is calculated by QM by PM. Right? Now what is QM? QM, right? This distance. So this distance is this one. Okay. Now if I put this one as A, this one as P, then QM is nothing but QB minus PA by PM. What is PM? This distance. PM is equal to AB. AB. Now we can write QB. What is QB? QB is F of C plus H minus PA. What is PA? This one, f of C. Okay. And what is AB then? AB is H. Remember this thing, the slope of the chord as f of C plus H minus f of C divided by H. Now comes the big picture. If Q is approaching towards P, suppose this Q, right? This Q is coming towards P like this. Okay. When it comes towards very close to P, very close, right? Very close to P, then what happens? Implies H becomes 0. Not becomes, H also tends to 0. It becomes H, this B point, no, this becomes here, P dash. Okay, this becomes very small. Then, if we need to calculate this value, then obviously we need to put limit over here. It is known by everybody. What is not known by everybody is that this chord will then, suppose imagine this is coming closer to P, then this chord will become a tangent at P, right? This chord will become a tangent at P. So QP chord will become tangent. Okay, this QP chord will become tangent at where? Tangent at P. Tangent at P. Okay, this is different. Tangent at P. Now, this time it's okay. Now, we need to find out. So, what we are calculating actually? We are calculating the slope of PQ. Slope of blank at blank is equal to what it is. If H is tending towards 0, then we can write it as limit H tends to 0 f of C plus H minus f of C by H. We can write this thing, no? Then see, we are calculating the slope of chord PQ. Now the PQ becomes tangent at this point. If the PQ is becoming tangent, then we are calculating slope of tangent. Slope of tangent to what? This curve f of x at x equal to what? X equal to this point, C. X equal to C. This gives this thing. That is the derivative. Now, if you write it more further clearly, you will be able to write, this comes here, you will be able to write f dash C, right? Where C is a certain point. Now, if you write this thing, suppose I am writing, okay? If you write it down, then what I have is the derivative of a function, f of x at x equal to a. Suppose we are giving it a, or suppose we are taking C, because we have used the example of C here. At x equal to C is slope of what? Tangent to curve f of x at x equal to C. Now, you need to mention the point, not x is equal to C, you need to mention at x is equal to C and f of C. This is the point. Okay? So correct the previous definition which I have written here, that it will be at certain point C and at C. Okay. Now by defining the different definition of differentiation and derivative, we complete today's video. So in the next video, we'll develop some formulas, we'll derive some formulas, okay, using this formula only, which we have derived today, that is f dash x is equal to limit of h tends to 0, f of x plus h minus f of x divided by h. So we'll use this formula in the next video to derive some really great problems, to derive some really great formulas, you can say. So see you in the next video.